Base pairing in DNA. The two sides of the DNA double helix are connected by pairs of bases adenine, thymine, cytosine, and guanine. Because of the geometric shape of these molecules, adenine bonds with thymine and cytosine bonds with guanine. Figure 1 shows the bonding of thymine and adenine. Each charge shown is plus minus E and the hydrogen-nitrogen distance is DHN 0.110 nanometers. Okay, so let's look at figure 1. Here is figure 1. This is adenine, this is thymine. You can see that we have a nitrogen-hydrogen-nitrogen bond here. So this nitrogen-hydrogen bond belongs to thymine molecule. This nitrogen belongs to adenine molecule. This is negatively charged. This is positively charged. This is negatively charged. The distance between two nitrogen ions is 0.3 nanometers. And we have oxygen minus belonging to thymine. This is bonding with hydrogen plus and nitrogen minus of the adenine molecule, and the distance between oxygen and nitrogen is 0.28 nanometers. All right. And figure 2 shows the bonding of cytosine and guanine. So that is going to be the second part of this question, so I will skip that for now. So part A, calculate the net force that thymine exerts on adenine. Is it attractive or repulsive? To keep the calculations fairly simple yet reasonable, consider only the forces due to the oxygen-hydrogen-nitrogen and the nitrogen-hydrogen-nitrogen combinations, assuming that these two combinations are parallel to each other. Remember, however, that in the oxygen-hydrogen-nitrogen set, the oxygen exerts a force on both the hydrogen plus and nitrogen minus, and likewise along the nitrogen-hydrogen-nitrogen set. So oxygen minus exerts a force on hydrogen plus and nitrogen minus, and this nitrogen minus exerts a force on hydrogen plus and nitrogen minus. So those are the forces we need to consider. And in part B, calculate the force on the electron in the hydrogen atom, which is 0.0529 nanometers from the proton. That's a 1 Bohr radius. Then compare the strength of the bonding force of the electron in the hydrogen with the bonding force of the adenine-thymine molecules. So let's start with adenine-thymine molecules. Okay, so we have oxygen minus here containing one electron, excess electron, and then we have hydrogen plus here containing one positive charge, excess proton, and nitrogen minus, one excess electron. So this is O minus, H plus, and N minus. And this hydrogen-nitrogen part belongs to the adenine molecule, so it's going to be on this side. And therefore, I show that this should be considered as a pair in interaction with O minus. And oxygen-hydrogen distance is 0.17 nanometers. So let me check. The oxygen, hydrogen, and hydrogen-nitrogen distances are 0.110 nanometers normally. Now, for the oxygen-nitrogen distance, we have 0.28 nanometers. Hydrogen-nitrogen distance, we have 0.11 nanometers. So that is the hydrogen-nitrogen distance. So we can say that this distance, oxygen-hydrogen distance, is 0.17, so that they add up to 0.28 nanometers. This is oxygen-nitrogen DON. Okay, and as for the nitrogen-hydrogen-nitrogen combination, we have N minus containing one excess electron, H plus containing one excess proton, and nitrogen minus here. This combination belongs to thymine, so it's going to be considered as a pair interacting with nitrogen minus. So this is basically showing me the boundary between adenine and thymine. The nitrogen-nitrogen distance is 0.3 nanometers. Nitrogen-hydrogen distance is 0.11 nanometers. Therefore, hydrogen-nitrogen distance is 0.19 nanometers. So that's what we can see here. So if we double check, we see that hydrogen-nitrogen distance is 0.11, this one. So we have this distance 0.19. So if I draw a free body diagram for the adenine molecule, considering the interactions of these parts with O- and nitrogen minus, hydrogen plus. Okay, so this O- exerts an attractive force on H+, so there is a force pointing to the left, O- H+ force, and O- nitrogen minus interaction is repulsive, so there is a force that is pointing to the right on adenine molecule. And for the nitrogen combination, nitrogen minus interaction is repulsive. A hydrogen plus nitrogen minus interaction is attractive for these two. So basically, those are the forces I have to consider acting on adenine. I'm not considering cross interactions between these two because they're far away from each other. That's what I'm assuming. So for simplicity, we're only assuming interactions on these linear parallel combinations. And so this is my x-axis and this is my y-axis, and I'm going to write the net force acting on adenine. Sum of the forces acting on adenine molecule is the force between O- and N-, and plus the force between N-, these are the repulsive parts in I hat direction, and then minus, I have the force between O- and H+, O- and H+, that is this force, which is attractive, and then we have H+ and minus, that is the force here, which is attractive. So this is going to be F H+ and minus in minus I hat direction. The distance between the hydrogen and nitrogen is the hydrogen plus and minus bond length. So that's what I'm calling the N here. And the force between oxygen and hydrogen is basically 1 over 4 pi epsilon 0 permittivity of free space E squared, the charge squared, divided by the distance between oxygen and hydrogen squared, DOH squared. So what was DOH? It is 0.170 nanometers. You can see here this. This is what I found in my analysis. Now DOH distance was found in this way. It's the distance between oxygen and nitrogen, which is 0.28 nanometers, minus the distance between hydrogen plus and nitrogen minus, which is minus DHN bond length. So this was 0.280 minus 0.110, which is 0.170 nanometers. The oxygen to nitrogen distance is 0.280 nanometers. That's shown in the figure. The distance between nitrogen minus and nitrogen minus, that's also given in the figure, 0.300 nanometers. The distance between hydrogen and nitrogen is the distance between nitrogen and nitrogen minus the distance of the hydrogen-nitrogen bond. So the length of the hydrogen-nitrogen bond, which is 0.3 minus 0.11, which is 0.190 nanometers. So you can see that all these distances are correct. So we have oxygen-hydrogen distance 0.170, oxygen-nitrogen 0.280, nitrogen-nitrogen 0.3, hydrogen-nitrogen 0.19. This is to keep this bond length 0.110 nanometers as given in the problem statement. All right. Now we can calculate the forces, the individual forces. So first one I have written is between oxygen and hydrogen. So that is 1 over 4 pi epsilon 0 E square over DOH square. That is the force that develops here. And then I have the force between oxygen and nitrogen. That is the force between these two, O minus and minus. And that force is 1 over 4 pi epsilon 0 in magnitude. It is the charge squared, E squared, divided by the distance ON, DON squared. The force between hydrogen and nitrogen, that is the force that develops between these two, hydrogen and nitrogen. That is 1 over 4 pi epsilon 0, Coulomb's constant. The charge squared, E squared, divided by D hydrogen nitrogen squared. This is not the bond length, but the distance between H plus and N minus I'm talking about, which was 0.19 nanometers. And then the nitrogen-nitrogen interaction. This gives me a repulsive force, FNN, that is equal to 1 over 4 pi epsilon 0 E squared divided by DNN squared. So the net force on the x-axis, Fx, is going to be FON plus FNN, FO minus N minus plus FN minus N minus, minus FOH, O minus H plus, minus FH plus N minus I hat. So remember, FOH is the force here, FNH is the force between these two. Okay, so this gives me net force is equal to E squared over 4 pi epsilon 0. Now I have to consider the distance between oxygen minus and nitrogen minus, 1 over DON squared. Then I have 1 over DNN squared. Then I have minus 1 over DOH squared. And then I have minus 1 over DHN squared. Once again, that's not the bond length, but it's the distance between H plus and N minus. So this gives me the answer that I'm looking for, the bonding force between adenine and thymine. So if I substitute the numbers here, remember that Coulomb's constant is approximately 9 times 10 to 9 Newton meter square over Coulomb square. That's 1 over 4 pi epsilon 0. Electron charge is 1.6 10 to minus 19 coulombs. So that's 1.6 10 to minus 19 squared, multiplied with the oxygen-nitrogen distance, DON, is 0.28 nanometers. That's this one here, 0.28 nanometers. So this is 0.28 10 to minus 9 meters squared plus 1 over nitrogen-nitrogen distance. That is given here, 0.3 nanometers. Here also, it is 0.3 10 to minus 9 parentheses squared, minus the attractive parts. We have 1 over oxygen-hydrogen distance. oxygen-hydrogen distance here is this distance, 0.17 nanometers, so that hydrogen-nitrogen bond length is 0.11 nanometers. So that gives me 0.17 10 to minus 9 squared. And finally, I have the hydrogen-nitrogen distance in this part, that is 0.19 nanometers, so that when you add to it the bond length 0.11, you get 0.3. So this is 0.19 10 to minus 9 parentheses squared. All right, and if you do the math here, the net force on the x-axis turns out to be minus 8.86 times 10 to minus 9 newtons I hat, and the minus sign basically indicates it's in minus I hat direction, that this is an attractive force that develops between these two molecules. It is the bonding force between these two molecules. For part B of the problem, let's remember what part B was. We want to calculate the force on the electron in the hydrogen atom in the first Bohr radius and compare it with the bonding force of the adenine-thymine molecule. Now, in the hydrogen atom in Bohr model, the electron is performing uniform circular motion around the nucleus, which has one proton plus E charge, and the electrical force between them is the centripetal force, and the radius is one Bohr radius in the 1s orbital, and that radius, Bohr radius, is 0.0529 nanometers. The electrical force between the electron and the proton is minus 1 over 4 pi epsilon 0 E square the product of the charges, it's going to be E squared divided by distance between them squared, A0 squared. It's in minus r hat direction. R hat is the radially outward vector. So substituting the numbers here, Coulomb's constant 9 times 10 to 9. As for the electron charge and proton charge, we have 1.6 10 to minus 19 coulombs squared. The distance between them 0.0529 10 to minus 9 meters squared. This gives us an electrical force between the electron and the proton minus 8.23 times 10 to minus 8 newtons. It's in minus r hat direction, indicating that this is also an attractive force. Now, we want to compare this bonding force with the force between thymine and adenine. So we see that the bonding force of the electron in the 1s orbital of the hydrogen atom is an order of magnitude higher than the bonding force between the adenine and thymine. Why do I say order of magnitude? This is 10 to minus 9, this is 10 to minus 8, so this is a stronger bond between the proton and the electron. The bonding force is an order of magnitude higher than that of the adenine and thymine. Okay, so in this problem, we looked at the bonding force between adenine and thymine molecules, considering that we only have oxygen, hydrogen, nitrogen, and nitrogen, hydrogen, nitrogen parts in interaction and forming parallel lines here on a line. So I call this axis the x-axis basically. This is attractive, this is repulsive, this is attractive, this is repulsive, and all of these were shown in the free body diagram here. And you can see that I have to figure out the distances between O minus and H plus and H plus and N minus, knowing that H plus N minus bond length is 0.11 nanometers. So we did that. This is 0.17, this is 0.19 nanometers. And then we have written all of the force components in terms of Coulomb's law, K Q square over R squared. And when we substitute the numbers that we obtained, we have an attractive interaction, a negative net force of minus 8.86 10 to minus 9 newtons. When we compare it with the electron in the 1s orbital of the hydrogen atom, which has one proton interacting with this electron, for the first Bohr radius, 0.0529 nanometers distance between them, and electron and proton charge, 1.610 to minus 19 coulombs with opposite signs, giving me an attractive interaction, I find 10 to minus 8 newtons instead of 10 to minus 9. So we see that the bonding force of the electron in the 1s orbital of hydrogen is an order of magnitude higher than that of the force between adenine and thymine molecules in this model.